Hey folks, welcome to another OpenNMS 101. If you'll remember in the very first module in this lesson, in this class, I talked about the four main parts of OpenNMS, four main parts. There is event management. And I think we've beaten event management to death. We've talked about event management, alarms, notifications, event translations, traps, the whole bit. So there's still some things we haven't talked about like syslog, things like that, but for the most part we've covered events. Another thing we talked about is provisioning. Now we've only kind of touched on provisioning. We provisioned our local host node, but we really haven't messed a tremendous amount with that. We'll probably save that for an extra lesson, but we have covered it to a large degree. We've had the service assurance. So we've talked about monitoring services. We did our example with our SNMP monitor, and we did an example with page sequence monitor. Now we're going to talk about the final piece of the main four, which is data collection, performance data collection. Now, OpenNMS has a number of different ways to collect and store data. On the back end, we started out, we used this thing called RRDTool. You're probably familiar with it if you've ever used Cacti or MITG or any number of tools that use this library. Toby Ediker, the guy who wrote it, it's a great little library. And so we started out using that back 15 years ago when OpenNMS started. And then we ran into some performance issues. So we found this library called Jrobin. It was done by this guy named Sasha Markovic in Bosnia. And Jrobin was a Java port of RRDTool 1.0. So we made Jrobin the default because OpenNMS is Java. By running it in Java, it made installs a little easier, etc. Now, Sasha stopped working on Jrobin, and he contributed the code to OpenNMS. But we really haven't had enough time to follow RRDTool. Meanwhile, Toby's been doing some great work with RRDTool, and we found that RRDTool is actually, for us, is a little better performing than Jrobin now. So we recommend that everyone uses RRDTool. Now by default, Jrobin will be installed. So we'll show you how to turn on, well, we turned on RRDTool in the installation guide. So you go into the RRDTool configuration and you enable RRDTool. Now, recently we added a new technology called Newts. When you're starting to deal with millions and millions and millions of data points, RRDTool just can't keep up. I'm not trying to disrespect RRDTool. I still use it as my default for pretty much everything, but we do have this ability if you need to monitor lots and lots and lots or collect lots and lots of data. You can use our new time series database built on Apache Cassandra, which is basically unlimited. If you can throw enough hardware at it and enough disks at it, you can collect anything. So those are our three main storage methods. Again, I recommend using RRDTool unless you're larger, and then I recommend running Newts. Now, for collection, we have support for the SNMP protocol, versions 1, 2, and 3. JMX, which is a Java management protocol. So if you have Java apps that expose management beans, we can use the JMX protocol to collect that. We can use HTTP. I love this collector. Probably do a chapter on this in OpenNMS 102, but basically you use regular expressions. You grab a web page, you parse it via regular expressions, grab numeric data off of it, and you get to store it in our system. Now, I've had people yell at me because you're not supposed to use regular expressions to parse HTTP. You're supposed to use the actual markup language that tags itself, the XML on which HTTP is based. So we have an XML collector where you can actually go and look for XML objects and collect data that way. If you're running Nagios, Nagios has an agent called NS Client. I believe it's on Windows. We can collect on that. The recommended way of collecting Windows data used to be WMI, the Windows Management Interface, but Microsoft being Microsoft, they've kind of deprecated that and limited what you can get, and now we can use something called WSMan, which is a protocol that is supported quite a bit with Microsoft products. And we also have SQL. So if you have a JDBC driver, a Java JDBC driver for the database you're using, you can drop that into the OpenNMS library and use that to actually make a JDBC connection and collect data. So I'm sure I'm probably forgetting some. We're adding new ones, but these are some of the basic. And the basic idea is You use these different protocols to identify a piece of information, you collect it, and you store that in a data source. And when you store that in a data source, from then on, everything else is the same. So I'm going to use SNMP as an example here, but no matter what you're using, basically you go out, you find that piece of information, you store it in a data source, and then everything else will follow. Now, this is going to seem to be a lot of work. And I don't think it's that much work, but a lot of people who are new may say, wow, this is a lot of work to do data collection. Now, the beauty of it is once you have set up how you're going to collect data. So if you say, I want to collect these metrics from a Windows box, I want to collect these metrics from a Juniper switch, etc., you don't have to do it again. It's automatic. So basically what will happen is OpenNMS will discover the device. As long as the service is discoverable and OpenNMS has permission to get this data, it's going to go out and grab this data, and you don't have to do anything. So yes, it may take a second to get your Windows systems exactly like you want it, but if you have 1,000 Windows systems, you're done. You don't have to go through and click through and say, oh, this is a Windows system, this is a Cisco router, this is a Juniper switch, etc. So that's what I like about it. Okay, now what can we do? We can do graphs. So you have your standard bits in, bits out. This is an interesting little graph on bandwidth. We have CPU statistics. This is one of my favorite graphs because the top line here represents the 15-minute load average, and the color underneath it represents the CPU utilization. So there's lots of cool things you can do there. And finally, I like Fresca. This is my Fresca. I like Fresca. So we have a soda machine that we use the HTTP collector to go and collect Fresca. So here's a year's worth of Fresca. So it tells me exactly where we go, and you can see where we've reloaded the Frescas when the lines jump up there. It means I've run out, and Tina, our office manager, gets a notice and says we're low on Fresca. She goes to the store, buys more Fresca, and puts it in the machine. Okay. Now, RRDTool. RRD stands for a round-robin database. And the way to think of it is, I always think of it as kind of this weird water wheel, that there are these little buckets. So you see this circle here, and you've got these little buckets. And each bucket represents a span of time. And you can put a value in each one of these little buckets. Now what happens is you're putting in values. So let's say we're at this green arrow here. The next one will go into that bucket. Then the next one will go into the one next to it, et cetera, et cetera, et cetera. When we get to the end where this red arrow is, that piece of data will be thrown away. And it'll be overwritten with the newest data. So the beauty of round-robin databases is that once they're created, they never expand. If anyone's ever had to add table space to a database, you know that can be a problem. So round-robin databases are kind of cool that way. The downside is the moment you create the database, it does take up disk space. And we'll talk about that when we show how these things are structured. But basically, when you install OpenNMS, if you're monitoring a bunch of devices, you're going to see the OpenNMS disk space increase fairly quickly on the system as it's going out and creating all these RRDs. And but once they are created, they'll never expand. So you don't have to worry about dealing with that. Now, you do have to choose kind of how you want to store this data, and we'll talk about that when we talk about how we set up the arrays that make up the database. And so because old data is discarded, you'll either need to dump or get a copy of the RRD database before that happens if you need to save that data, or you'll need to make it bigger. Now, making it bigger, etc. The database structure consists of RRDs consist of these things called round-robin arrays. And a round-robin array and the step size make up the database. Now, the step size is how wide your bucket is. And this will represent, for this particular RRD, the highest granularity of data you can store. In OpenNMS, by default, it's 5 minutes. So we will have a bucket that's 5 minutes long, which means every 5 minutes we can store one particular value. Now, what are our values? Well, you have a number of these things called round-robin arrays. And they're in this particular format. Now, the consolidation function, the CF here, so you have RRA, that's a string. RRA, you've got this consolidation function. And this is one of average, min, max, or last. So basically what will happen is as you're putting information into your bucket, it'll take either the time value average of that value, it'll store the minimum of multiple values, the maximum of multiple values, or the last value. Now we're going to set up OpenNMS so that it actually collects one value per step. So you could use any of these. You could use average, min, max, or last. But in the case of when we create bigger buckets, when we create bigger RRAs, we'll take average, min, max value of a set of steps. It's become clear in a second. I don't think I'm doing this very well, but we'll cover it when we show you an example. Let's skip this XFF, the X files factor, for the time being. Steps. So how many steps are in the RA, and then how many rows are in the RA? So let's just jump to the example. Okay. So if you'll remember, I once said that OpenNMS stores time in milliseconds, always refers to time in milliseconds, with the exception of one thing, and that is RDs. The most granular RD you can make is 1 second. And so here we have this RD step here of 300, says our bucket, our step size is going to be 300 seconds or 5 minutes. So in OpenNMS speak, we usually use 300,000 for the step for the milliseconds. But in this case, the finest granularity we can get is 1 second, which is a 1 here for your step size. We're going to use 300. So this is our bucket is going to be 5 minutes long. And now what we're going to do is we're going to take the average value of 1 step and we're going to store it 2,016 times. Well, it turns out that's the number of samples, 5-minute samples in a week. So if you take 12 samples per hour times 24 hours in a day times 7 days, you get 2,016 samples. So we're going to store as polled data for a week. Now, we're going to create another RA. We're going to take the average value of 288 steps for, excuse me, I'm looking at the wrong one. We're going to take this RRA, which is we're going to store 12 steps for 1,488 rows. Well, it turns out 1,488 is the number of hours in 62 days, or 2 months. That was what we were aiming for, 2 months. So this line here, this RRA line, is we're going to store as polled values, so 5-minute samples for 7 days, 2,016 times. Then we want to store hourly samples. So we'll take 12 steps. So 12 steps is an hour. So 5-minute steps times 12 is 60 minutes. And we want to store that 1,488 times, which is the number of hours in 2 months. And then we want to take the average and min and max values and store them at a grouping of 288 steps. 288 steps is the number of steps in a day. So if you take 12 steps per hour, 24 hours in a day, you get 288. And we want to store this for 366 days. So basically what we're going to do is we're going to store as polled values for a week, hourly samples for 2 months, and then daily samples for a year. And what does this mean? So it's the granularity. So here I'm storing, this is over a month, and I'm storing days. You can see here's week, this is 4 weeks. And so I'm storing samples here. These are hourly samples. And if you look, it's very, very granular. But if I zoomed in here, I would see that these values here are actually hourly samples. But I don't really care about the 5-minute samples back here 4 weeks ago. I care about it now. And if I zoomed in over here, I would see the data that we have in 5-minute samples. Now take a look at my Fresca thing. This is over a year. And so if I looked back here in more than 2 months, if I look somewhere in here, I'm going to just see daily samples. It'll tell me the average number of cans that were in the machine for that particular day. Again, when I'm looking at the scale of a year, it looks very, very detailed. But it turns out that we've done this consolidation function where we have actually stored 5-minute samples, then hourly samples, and then daily samples. Why is this important? Well, it turns out that each one of these things takes up disk space. I think this is around 30K. I forget the exact, so 30 kilobits for a 40 kilobytes, excuse me, for one RRD database for a year. And that's not much. That's really not much space. But if I were to increase it, it ends up creating bigger and bigger RRD files. The biggest performance bottleneck in OpenNMS comes from this storing data, performance data. We're having to open up a file, add a value, and close the file and store it. And disk systems, especially if you're trying to do 1 million of these, they're just not fast enough. You can fix this with nice big write caches. You can use some sort of network attached storage. But it comes down to it, you're eventually going to hit this physical wall that the disks just aren't fast enough to collect all this data. And so you really want to kind of balance. If you wanted to store this data for several years, you're going to end up increasing greatly. When we started, we used to store as polled values for 2 months and then hourly samples for the year. And the file was 283K. And this was like 15 years ago. And so the problem was when you're dealing with people, dealing with disk systems that were 15 years old, it was rare you could find someone. And they would compare OpenNMS negatively to other tools like MRTG. If you look at MRTG, its consolidation functions are much more aggressive than OpenNMS. They store even less data. I think they're doing like as polled for 1 or 2 days and then half-hour samples for a week. So again, the more rows you have here. So if I increase the number of rows, I'm going to increase the size of the RRD files. We create one RRD per value. And so you're going to greatly increase the size of this, and it's going to really impact your disk system. Hey, if you have it, great. You can go out and buy SSDs. You can put a big write cache on it. But if you can't, there's other options. And namely, the option I want to talk about, well, let me get down here. I don't have it, is Newts. So if you do find yourself in a situation where the disks just won't keep up, set up a Cassandra cluster and use Newts. Now, getting back to RRD, so you can do this tool called RRD. You can run this command called RRDTool dump, and you can point it at a file, and it'll dump into XML this. So here is your timestamp, and here's your value. So at a step size of 1, we're getting 1 every 5 minutes. So there's 1 at 6, there's 1 at 6:05, 1 at 6:10, etc. Now, this will list the RRA for 2016 rows, because that's the number of rows we store in our RRD file. Then we're going to have, 1,488 rows of hourly samples. And if you look into that RRA, you'll see that the timestamp, each bucket is an hour wide. So there's a 3 o'clock bucket, a 4 o'clock bucket, etc. And then for the daily samples, the step size of 288, we'll have 3 RRAs that do min, max, and average of the daily values. So as you can see here, there's one on the 4th, one on the 5th, one on the 6th, etc. And so this kind of shows you this deal. Now, I mentioned this thing called the X files factor, which I was talking about. When we are getting ready to create this 12-step value from the previous hour's samples, the X files factor determines how many of those can be null. So RRDTool uses this idea of, it's called NaN, not a number, and it's null, basically. There's no value there. So let's say I'm monitoring a network device and it goes down. And let's say it's down for like 15 minutes, so I lose 3 polls. So out of my 12, I only have 9. Should I consolidate those 9 values and stick them in the hourly RRD, or should I just discard it? And that's what the X files factor does. So we use an X files factor of 0.5, which is 50%. And so at 50%, this means that if I have, for the hourly rollup, I have to have 6 values that are valid. If I have 6 values that are valid, I'll consider that acceptable. I'll take the average and I'll store it. If I only have 5, I'm going to store a NaN. Same thing for the daily samples. If it's down for half a day, as long as I have 144 samples, I will consolidate that and stick that in the RRD. But if I only have 143 or less, I'm going to stick a NaN. This NaN happened to be, I think, when I took the snapshot, I just hadn't run it for 2 days when I made the slide. But it will reflect a NaN if there's not enough. So this is probably the most complex thing to get your brain around. So you've got these RRD files, which are round-robin databases, which consist of a step size and these round-robin arrays. The step size is how what is the most granular bucket, if you will? What is the most granular data structure that I can get? And in this case, it's 5 minutes. And then round robin arrays show you how you take this data and can consolidate it. So you can have round robin arrays that are as polled, like we do, or you can roll it up into hourly samples, or you can roll it up into daily samples. And so by default, we do as polled for 7 days, we do hourly samples for 2 months, and we do a year, min-max and average for a year, daily samples. Now, if you're in countries that the decimal is indicated by a comma, and you're using a localized version of RRDTool, you'll need to edit everywhere you get these little RRD files and put in commas here. Everybody sees little RRD sections. This was actually in, if you remember, in the top of the polar configuration file, and I said we'd skip it because we store latency data using RRDs as well. Now, where do we store these files? Well, it should be stored in opt OpenNMS share RRD. Usually that's a symlink to either var OpenNMS or var lib OpenNMS, depending on your distribution. Now, under this directory, response time values are stored under the IP address. So if we're polling a particular device, we're going to poll it by IP address, so it's okay to store it under IP address. If the IP address moves, so if I actually, maybe I have a web server and I go get a more powerful web server, IP address changes, we will have the historic latency data for the old server, and then we'll just start collecting on the new server. Now, for SNMP and pretty much everything else, we store it by node ID. Things can change. MAC addresses can change, IP addresses can change, host names can change, etc. So by default, we store it by node ID. So the first node will be node 1, the second node will be node 2, etc. Now you can also choose to store it by foreign source foreign ID, and this can be useful, especially if you have multiple systems and you want to compare them. Foreign source foreign ID is another way of storing this, and you can enable it in our properties file. So we have so for node 1 we would have opt OpenNMS share RRD /SNMP/1, where 1 is node ID 1. Node level data would be stored at the top level directory. Interface data is going to be stored in a specially labeled directory based upon the interface description. And then we have this thing called generic resource data, which I'll talk about in a second. So this is off of one of my systems. If I actually go here and do a list under opt OpenNMS share RRD response, I'm going to see subdirectories that are IP based. So these are all the IPv4 addresses. Here's a bunch of IPv6 addresses. We store those in separate directories. And if we actually do a list on one of the directories, you'll see, well, there's HTTP, there's HTTPS, ICP. This is all the response time data. These are the little RRD files here. This meta is actually used for something called the near real-time grapher, which I'll talk about at the end of this lesson. But these RRD files are where we create them. So if you wanted to look at the latency data for the HTTP service on this interface, you would look at it here, HTTPS is here, etc. Now, the reason we create all these subdirectories is we may have multiple http.rd files, multiple icmp.rd files, etc., and we need to separate them. Otherwise, we will just keep overwriting the same file, and that's not good. Now, for other data, it's kind of a misnomer to call it SNMP because we'll store other data here as well, like HTTP data. But SNMP data is based upon node IDs. So here's a whole bunch of nodes. There's node 1, there's node 10, there's node 100, 101, 103, etc. These are all directories for each device in this particular OpenNMS installation. And if I were to list something here, you will see here are all of the, this is a Juniper device. And as you can see, there's all of these node level data. So these are scalars. If you remember from our SNMP discussion, scalars are items that pretty much exist only once. So the number of ICMP packets, that's for the system as a whole. TCP, for the system as a whole. All these Juniper devices, the buffers and CPU utilization and temperature, for the device as a whole. So all of those go in the top level directory for node, in this case, 66. Now, interface data. So in this node 66, we have all these interfaces. These are all the different interfaces on my SRX. And so as you can see, each interface is going to have its own directory because the actual files are going to have the same name. And we don't want to overwrite the particular files. So as you can see here, we have the high capacity broadcast packets, high capacity inoctets, discards, errors. All of this is under the VLAN 0 interface, a subdirectory. And then we also have for VLAN 1. So we'll have all the different stats for VLAN 1. So we'll have a directory for each one of these. So all these GEs, etc., will have, these gigabit Ethernet interfaces will all have their own subdirectory with their information in it. Now, we use the interface description, and that worked really well for a while until we found a vendor who labeled all of its interfaces switch port. So if you had a 24-port switch, you would end up having one subdirectory called switch port, and you'd have a bunch of useless data. So we added the MAC address. So we end up with the actual interface description and its MAC address, and we found that was unique. This is hard-coded into OpenNMS. One of these days, I want to be able to change it. Because when OpenNMS started, there were only two ways you could store data. You could store it as a scalar, so it would be in node-level data, or you could store it in an interface. Now, what happens if I want to monitor, I don't know, disk drives? So NetSNMP has a disk table which stores all of the disk information. And so I jumped over here to node 97, which has this disk index. We call this a generic resource. So we enabled the ability to actually write generic resources. And in this case, we have one for root, we have one for boot, and we have one for home, because these are the systems that I happen to have on this particular device. So as you can see, we have this is the generic resource. And so if I have 30, if I've configured my NetSNMP to report on 30 mount points, I'm going to have 30 directories here. If I only had 2 mount points, I would have 2 directories here. Now, it used to be what I'd have to do is actually, I would say, okay, here's disk 1, here's disk 2, here's disk 3, here's disk 4, and they would all get stored up here in the top level directory. Well, that was a pain, because if someone added a disk or anything like that, you had to go back through and re-add it. So in this case, with the generic resource, it'll just automatically find the instance for us. Oh, here's my Newts slide. So finally I get my Newts slide. I need to move that up. So Newts data storage is totally different. Newts uses Apache Cassandra. We store the value exactly as collected. When we actually do this RRA here, it's going to give us a time value average. Like I had a customer once who said, hey, it said that there were 3.5 users logged in. You know, how do I get half a user? And I explained to him, let's say at noon, 12 o'clock, there's 3 users logged in. And at 12:02 and 30 seconds, we get another user logs in, so we have 4. So for that 5-minute bucket from 12 o'clock to 12:05, what should I store in there? Should I store a 3, because that was half the time it was a 3? Should I store a 4, because half the time it was a 4? Well, if you choose average, in that instance, you would choose 3.5, because the average number of the time value average of the people logged in was 3.5. Or I could choose min, which would have stored a 3. I could use max, which would have stored a 4. Or I could use last, which in this case would store a 4. I tend to only use last for things like temperature. But for me, average works pretty well. Since we're only putting one value in, average tends to be okay. But if you really care about the exact value that's collected and not the time series value, you can use Newts, because Newts does no consolidation. So any kind of consolidation or averaging, etc., that you need to do, you can do it by taking the data out of Newts. All Newts is concerned about is storing data as fast as possible. Make sense? Okay, so let's review this. So what do we get out of this so far? OpenNMS creates these round-robin databases. We create one for every value. Now, the reason we do one for every value is that once you create an RRD, it's very, very, very difficult to change. In many cases, it's just, I'm not saying it's impossible, but in many cases, it's just easier to blow away the existing data and create new. So if we had some values that we were collecting and then we wanted to add a new one, because we used to do this back in the day when OpenNMS was just starting, we did one RRD per node. And the problem was if you wanted to add a new value to that node, it was difficult because if the RRD is already created, it was very, very difficult. You can dump it and re-add it, but there's a lot of overhead and it's not fast. So what we ended up doing was saying, okay, we'll create an RRD for every value. And that's great because if one gets corrupted, you just delete that file, it gets recreated, etc. So we create one. It does create a whole bunch of files, but you can also but the reason why we don't change it is it's just difficult to change. So if you wanted to come in here and store 2 years of data and you wanted to change this 366 to something else, you'd have to go and either dump and restore all of your RRDs, or you would need to just blow them away and create new ones. So be thinking about what your needs are. Remember that if you increase these at all, you are going to add more load to your disk subsystem. But once you create these RRDs, they're hard to change. So be thinking about the type of information you need. If I had to make one change to OpenNMS, I would probably have added an extra day here. So I probably would have added another 144 samples. 288 samples to this number here, just to have an extra day. So I have 8 days. But this has been in place for so long, I'm not going to change it. So you can use the RRDTool dump command to look at the RRD files. Everything is stored in opt-OpenNMS share RRD, which is usually a symlink to something under var. Response time data is restored under IP address, be it IPv4 or IPv6. Every other data is stored under a node ID, or if you configure it, a foreign source and foreign ID. Node level data is stored at the top of the file. So things that exist once are stored at the top of the file. Things that have multiple data points with the same name have to be stored in subdirectories. There's a special type of subdirectory called an interface, an IF index subdirectory, which is made up of the interface description and the MAC address, the combination of those two. Also, we have this ability to do generic resources. This works great for tables. So if you have a fan table or environment table or a disk table where you want to collect on many things that may not have any instances whatsoever, or may have 20, may have 30, use a generic resource. And we're going to talk about that in the configuration. And then if you have to collect so much data that RRDTool just doesn't work for you, use Newts. And you can go to newts.io is the website that talks about the project. We build Newts in, so you don't have to do anything. You don't have to download any extra software. Basically, you go in, enable Newts, and point it at a Cassandra cluster. And I do plan to do a lesson for that in the future. Okay, data collection. All performance data collection is controlled by controlled by a daemon called collectd, and we configure it in a file called collectd-configuration. For each particular protocol, you have a so collectd is responsible for the overall what services am I collecting on. The specific information I'm collecting using those services, those protocols, is in special files. So SNMP was our first one, so it's in data collection config.xml. For HTTP data, which is going to use regular expressions to parse a file and gather information, that's in HTTP data collection. JMX, which collects management bean information, is under JMX data collection configuration, etc. There's an XML data collection config, blah, 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 blah. So, since these files can get kind of complicated, we've stored the individual configuration files, especially for SNMP data collection, in a specific subdirectory. In our case, is data collection is the name. So opt OpenNMS etc data collection. If you remember when we were talking about events, we have event conf, and then we have the individual event files, which are in the /events directory. Same idea. So we've got data collection config, points is like event conf. It points to files in the data collection subdirectory. Okay, here's an example of collectd-configuration. This package, remember you can have packages. So we can have the example one package is our default package. You can have filters and include ranges, again, just like the polar configuration. In fact, in the very, very beginning, there wasn't a collection daemon. It was done during polling. But it turns out that collection can take a long time and polling needs to be short, so we broke them out. But they have a very, very similar ancestry, and so they have similar configuration files. So for our SNMP service, we're going to collect every 5 minutes. Again, time in OpenNMS is in milliseconds, so 300,000 milliseconds is 300 seconds is 5 minutes. The one exception being the step size in RRDTool. So there's parameters, just like our other services. The parameter here points to what collection schema. I would use the word group, but we overuse the word group in OpenNMS, so the collection schema that we're going to use, in this case, it's the default schema. So we're actually going to go into the data collection config file, look for a schema called default, and then look for configuration in there. Same thing for WMI, WSMan. They have their own configuration files and their own schemas. And just like the polar configuration, if you happen to add a new service that you want to collect on, be sure to add a collector tag at the bottom of the collectd configuration file that points to what software you're going to use. So in this case, the SNMP service uses the SNMP collector, the WMI service uses the WMI collector, and the WSMan service uses the WSMan collector. I'm going to go over this, so bear with me. So I mentioned that back here, that SNMP data collection is controlled by this data collection config file. So collectd says, hey, if you're running the SNMP service, use the default collection schema. That collection schema is defined in the data collection config.xml file. Again, I have an open bug to rename this the SNMP data collection config file. So collection name here is default. So this is our schema. So default collection name. Here's my RRD steps. So if I wanted to say, let's say I had a need where I needed to collect data every 10 seconds or every minute. Well, by default here, we create this polling interval for in collectd for SNMP is 5 minutes. The step size is 5 minutes. Now I could poll faster, but if I polled faster, all I'm going to end up doing is adding, there'll be more consolidation here at this step function. We're not going to store any more granular data. To do that, I have to change the RRD step. So one of the things I could do is go over here and create a new package that pointed to a different schema, a schema other than default, which had a different set of RRDs. Now the next part, and the only other part in this, is these data collection group names. This is that information I was telling you about that was in the data collection file. So group files are stored in the data collection subdirectory. So for SNMP, and SNMP only, there are three things. We basically collect object IDs. So SNMP objects are identified by object IDs, and they're going to have the stuff we're interested in. They're going to have the amount of traffic going in, the amount of traffic going out, the errors, the temperature, the disk space. That's going to be an object ID. So we create object IDs and associate them into groups, and then we assign the groups to the system object IDs. If you remember, the system OID is a specific object ID that identifies what type of device we're monitoring. So if I'm monitoring a Microsoft Windows server, I'm going to have a specific system object ID, and then I can point to groups that have the object IDs I'm interested in. Now the only weird thing, the other thing we have to do is, if we're using a generic resource, we have to define it in this file as well. So we've got our system definitions, which are triggered by a system object ID that point to specific groups of object IDs to collect. Generic resources are used to extend groups so that the instance we are collecting on can be a variable. Otherwise, I have to hard code it. So there's a number, like I could put in 0, 1, 2, 3, 4. I could put in IF-index, which is a special instance, or I could put in a generic resource. Okay. So here in MIB2, I'm going to talk about the MIB2 group. MIB2, if you remember, is Management Information Base 2. It's the standard. And so every system object ID should start out with .1.3.6.1.4.1 something. Notice that this is a system definition tag which exists in this file. And we call this one Enterprise. And the system object ID mask says if the system object ID for the device starts with .1.3.6.1.4.1 something, it'll match this system definition, and we will try to collect on MIB2 interfaces, MIB2 TCP information, and MIB2 power over Ethernet information. if those object IDs exist on the device, we will just automatically start collecting on it. Now notice that the reason we do a starts with is this word mask. If I had just had system object ID and I ended it, the system object ID would have to match exactly. But in this case, it's a system object ID mask, so it starts with. Make sense? So let's look at some of these groups here. So here's the TCP group. So active opens, passive opens, attempt failures, current established connections, etc. These are all scalars. So they have an instance that exists as a number. In this case, the instance is 0. So the number of current established connections is there's just one value for the whole device. And I picked on this because when I first added this to OpenNMS, I screwed up and I used a counter here instead of a gauge. And that was wrong. You don't want to use counters. I talked about this in the SNMP module. But basically what ended up happening is if I had, say, 10 connections and one of the connections dropped, so I went from 9, a gauge says, oh, I had 10, now I have 9. A counter says, oh, I have 10, now that I'm at 9, I must have had 2 to the 32 minus 1 connections come in, and that's why I wrapped around. And so I ended up having to change this from counter to gauge, and then I had people go and delete their RRD files so that they would regenerate and have the right data in. Once you create an RRD file, you can't change it. So you have to basically dump it, recreate the file, and restore the data. Now, here is my IF index one. If you remember, I told you IF index is a special index based upon the interface description and the MAC address. And so here's for this Juniper switch, here are the gigabit Ethernet and some of the VLAN information for these particular ones, and there will be subdirectories. And so that index, to create that, I use IF index as my instance. So basically it'll go and look for .1.3.6.1.2.1.2.2.1.2.2. Anything after that will be stored as the IF index for that particular value. Now, since we don't want to modify existing interface groups, because one of the options you have with OpenNMS is instead of storing by individual files for each value, you can store each group in one file. For some people, they see better performance that way. I really don't know if that's still the case, but we put it in there anyway. And so if you modified this group, it wouldn't work on nodes that already had an RRD based upon MIB2 interfaces. And so we don't like you to modify groups. Instead, we just create a new group. In this case, this is the high capacity in and out octets. So, and this came up. We add this to things like routers. If you want the high capacity, the 64-bit object IDs for everything, then you need to go back here and add MIB2-X interfaces to your enterprise group. If you search through the configuration files, you'll see that a number of things like Cisco routers and Juniper devices have MIB2-X interfaces as a default group. But we did not do that at the enterprise level. Now, so the last thing I wanted to talk about was a generic resource. And in this case, it's the, it's host resources. So the host resources table is a MIB2. It's a standard table, so it starts off .1.3.6.1.2.1, 2 being MIB2. .25 is the host resources branch. And we want to store the type, the description, how big it is, the units, so this is going to be in gigabits or megabits or terabits, etc. How big it is and how much is being used. So we're going to store these 5 values. So we want to collect this. Notice this instance. So basically what's going to happen is when OpenNMS goes and it'll try to walk .1.3.6.1.2.1.25.2.3.1.2, anything after that, anything, is going to be considered the instance. And if I'm not using numbers, which are our scalar instances, if I'm not using IF index, then I have to define these generic resources. So So these generic resources actually show up here. So at the top of the file, I have these resource types. And here you can see HR storage non-unique. So it basically just uses the index storing strategy. And it basically says, hey, I'm going to take the index. And oh, by the way, when I grab this string here, this HR storage description, I'm going to use that as part of the resource label, which means that I can look at things. So if I go back here, if we go back to our disk, oh, where is it? If I go back to our disk here, we've used this underscore root file systems, boot, and home to identify the instance here versus just the index number, which might just be 1, 2, 3, 4, 5, and they may change. So if we do it this way, we know that it'll always track. So if the index changes, we're going to use the description as the storage directory and not the different, not just the raw index. Now, this is a simple one. So you don't have to have this HR storage description. You can just use an index. Most of our generic resources are just index storage strategy. So all they do is basically whatever comes after the final number here, we just use that as the index. But in the case of disk drives, it helps to know what the heck I'm looking at, from a drop-down menu. I might want to say, hey, is this the root file system? Is this a boot file system? The index of 3 may not help me. So we can use, in this case, we can use a different type of storage index called the sibling column storage strategy, which allows you to take a particular value, in this case, the HR storage description file, and actually use it instead of just the simple index storage strategy. So we're using the sibling column storage strategy. So the sibling column in this case is the storage description. Now the problem is I might have slashes or strange characters like colons in the case of a Windows box in my system, so I want to be able to strip those out. So you're able to add these replace parameters to actually go, hey, if this thing here is blank, then make it, if it's just slash, then make it root file system. Otherwise, remove all the slashes, remove all the spaces, remove all the colons, and then whatever's left becomes the index name. It's not as hard as it sounds. I mean, I'm sitting here listening and say, this sounds really complex, but it really isn't hard. When I add, when I need to add a table, I just go in and grab this, just the index storage strategy as a starting point. And usually that's enough. I am planning on doing an entire class. It'll be the first one in the OpenNMS 102 class series, which will be the standalone episodes on using our MIB compiler. And I will talk about that at length there, about how to use these generic resources. But the generic resources are used when you have to use a special index and you want to define it. The simple ones are this index storage strategy, which actually is just pretty much a number. And in this case, the storage index is much more complex. We actually use a name so that it tracks. The NetSNMP disk index uses the same strategy. So this here is a sibling column strategy and not a simple strategy. Okay, so we have scalar groups, which happen to have a single number. We have IF index groups, which are based upon IF index, and then we have our generic resource groups. And we tie those all together with a system definition. Now this name, whatever you use for your name, you want it to be unique. And I'm going to talk about that in our example. If you had the same name, then it can cause some problems. Okay. So, mention the exercise. So what we are going to do is we are going to create a new SNMP. Remember how we used the SNMP extend? We had our class monitor script. We're going to create a new script called class collect that instead of returning OK, returns a number. And then we're going to add that to our NetSNMP configuration, and we're going to use that to data collect. And then what we're going to do, so we'll do that, and then we're going to add a new object ID and a new system definition. Then we'll add that to the data collection config, and then we'll verify that data is being created. Okay, so I know we're not all programmers, so don't get too upset. We're going to do this very, very, it's more complex than our last one, but it should be a very, very simple script to generate a random number. So here I am on my system. I'm going to edit. Let's do edit temp. Let's just go to temp. So let's look at class collect.shell. I'm going to use bin bash. Again, to remind you, you have to set the shell, because while the script will work fine if you're already in a shell, SNMP doesn't run in a shell. It doesn't do a fork exec like other check scripts do. It just goes ahead and executes the command. So unless you set your shell environment, it won't work. And so I'm going to use echo $random. I'll save that. Save that. I will do a chmod plus X to make it executable. And if I run it, you'll see that, yay, I've got random numbers. Now I have to edit etc snmp snmpd.conf. I'll go to the very bottom. There's our extend class monitor. Do not do this on your, if you've been following all these lessons, don't uncomment this, but I'm gonna, don't comment this out. I'm gonna comment it out though, because I'm gonna do some walks and it'll just be a little cleaner. So I'm gonna extend class collect to be temp class collect.sh. And now I'll restart SNMPD to make the changes take effect. And then if I do an SNMP walk, -v2c -cyru so no z localhost .1.3.6.1.4.1.8072.1.3.2 ta-da! I have run the command. Now notice this, permission denied, permission denied, permission denied. This drives me crazy. I don't know how to fix it. It's SE Linux. For apparently I'm not able to run things in temp. It's an SE Linux thing. SE Linux is black magic to me, so I'm going to do set enforce equals 0, and then when I run it, I get my values. So as you can see, let me clear this out. So as you see, number of entries is 1. I'm going to run the class collect shell script. It's going to cache it for 5 seconds. The first line of output is this number. The second line of output is the output in full is just one line with this number. There's only one line. There's no errors, and the very first instance here is this value. If I had multiple lines, I would have a multiple instance here, multiple indexes. You know, .1, .2, .3, .4, .5. So I'm going to run this again with the dash capital O-N, which is numeric. And so as you can see, now it's this numeric number. If you remember from our class, this here spells out class collect. 99 is a lowercase c in ASCII, L is 108, A is 97 because that's 2 ahead of C, SS collect. So this spells out class collect, which means if I actually did turn on that extend, so if I edit this file and I get rid of the extend, I'm going to be able to actually get, I will be able to get both of them. So let me clear this. And so now you'll see the number of entries equal 2, and then we have the class collect instance, and then we have the class monitor instance. Does that make sense? The instance is this bit here. I don't quite know what the 12 is, if it's obviously some kind of control character. But basically the instance is this stuff here. And so OpenNMS can actually, you can configure a generic resource to say, hey, collect on this value with that instance, and it would collect 2 or 3 or 4 or 5, no matter what you have. The thing I like about extend, because it builds the name into the object ID, it's very, very cool because it will, let's say I have 10 scripts, 2 run on this system, 5 run on this system, etc. It allows me to discover who's running as well. So now that I have this running, remember, so I'm able to actually get a value here, this 1 in this case, it's time to add it to OpenNMS. So let's go back to the slides. So we've created, we've done our extend, we've restarted SNMPD, we've verified it happened, we've now got our class collect. Now we need to define that object ID in a file. So I'm going to go to my browser, and I'm going to go to www.opennms.org/training. I'm going to jump into the config subdirectory, grab exercise 11, and I'm going to grab this class group file. So I'm going to take that, copy the link location, and I'm going to go back over here, and I'm going to go to opt OpenNMS etc data collection, because that's where those group files are stored. If I do a list, you can see there's a number of them. Here's the Fortinet information. Here's Brocade, AKCP. Here are collections we have for all these different varieties. We've got Cisco, Juniper, etc. This works out of the box. So if you have OpenNMS configured, SNMP configured on OpenNMS, you discover a device, it should automatically collect this information. So I'm going to do a wget on this class group file, which now puts it there. And let me look at it. So if I cat class group file, you'll see that I call this group the class object IDs, and there's this long object ID. Remember, this is the class collect right here, CLA collect instance.1, and I'm going to store it in a data source name, which we call an alias, called class random. So it should create a file called classrandom.rrd. And the type is an integer. Here's where I'd put integer, counter, gauge, etc. Now, I'm going to define the system definition. I know that this is going to come from a NetSNMP system, so I'm going to use the system object ID mask of 03614111361418072. Anything matches that, starts with that, we'll try to collect on the class object IDs, which in this case will be this guy. Makes sense. So it says, hey, if I have SNMP running and I have an object ID that starts, a system object ID that starts with this string, I'm going to try to collect on this object ID. Now notice this collection group is called group for class. Nothing will happen until I edit. I'm going to go up one directory and let me edit the data collection config file. So this was in the data collection subdirectory. We added this class group file. I'm going to go into data collection config. Here is my default. Here's my default schema right here. And I'm going to go down to the bottom here. And I am going to I screwed up. Undo. Group for class. I'm going to put that name in and I'm going to save it. Now, assuming I did everything right, I should not have to restart OpenNMS. So, while we're waiting, because it'll take up to 5 minutes for this to happen, let's kind of go over in the configuration files what we're doing here. So we have our localhost node. On that localhost node is SNMP. So if I go and I look at localhost, so here's localhost. Notice this outage. Anyone know why that outage is there? It's because I had used the, I had rebooted this system since the last time I took the lesson, and so SE Linux kicked back in, set enforce was in, so SE Linux was in force. I was unable to get information from this particular object ID, so it was marked as down. When I changed set enforce equal to 0, it enabled us to collect on that information, etc. Now you would probably put any information you were doing this, something like var, something that was allowed to run executables, or you can edit your SNMP configuration, your SE Linux configuration to do that. Anyway, so we notice that the system, we have SNMP enabled on here, and we have a system object ID of 1.3.6.1.4.1.8072.3.2.10. So jumping back here, I'm going to look at collectd, and so if I look at collectd, we happen to have a package called example1 in which we have this service SNMP. So, hey, if you're a node with the SNMP service, you're going to look at the default collection schema. So that's in collectd, and then at the very bottom, you can see all these different collectors. SNMP uses the SNMP collector. So for the SNMP collector, I'm going to go to data collection config.xml, and I'm going to look for the default collection name, and I'm going to try and collect on all these groups. Now at the bottom, we added our group for class. So we've got our group for class data collection group reference there, which means we'll go to the data collection subdirectory and we'll look for the group for class file, which says, hey, if my system object ID matches this, which it does, it's .1.3.6.1.4.1.8.72.3.2.10, so it matches, then I'm going to try and collect on that object ID. And if I do, I'm going to store it in a file called class_random.rrd. Make sense? Okay, since this is node 1, and I can tell by going up here, and you can see node ID 1, node ID 1. So localhost is node ID 1. So I'm going to go to opt OpenNMS share RRD SNMP1 and do a list. And as you can see, there is my class random RRD file. So it's working. Now if I do an RRDTool dump on class_random.rrd, we pipe it to more, you'll get this XML file which tells me what the last value was. In this case it's 26781. Oh, that's the yeah, and then that's the timestamp. I think that's the timestamp. We've got our step size, which is right there, and then as you can see, we have this goes back a week. So I'm writing this on April 3rd, so a week ago was March 27th. So you can see there's 5-minute buckets for a week ago. We can zoom ahead, zoom up a little bit. As you can see, it takes 5 minutes for the first sample to be stored, so we haven't stored anything yet. That's one of the reasons I'm talking right now, because I'm enabling graphs to start up, or data to be collected. And then we have the next RRA, which is the hourly samples. And then we'll go to we have 3 daily sample RRD files. Oh, you can tell when daylight savings time, so this daylight savings time kicks in. Cute, huh? Okay, let's go back. Now, I'm collecting data every 5 seconds. When I originally did this class, I actually set it up to collect every 30 seconds, but that required adding new data collection groups, etc. And I just decided to save that for a special lesson, because I think I'm throwing a lot at you here. This isn't as hard as it looks. It really isn't. But all you got to do is keep it. Once you do 1 or 2 of these, it becomes old hat. It's real easy for me to add information to the system. So, okay, so we grabbed our class group file. We added it to the data collection config. The file itself consisted of our long object ID with our instance of 1, which goes back to this guy. This is our long object ID with the instance of 1. So I just copied it from here. If I had multiple lines, I could put 1, 2, 3, 4 here, or I could create a generic resource, which would create that for me. Then we added the data collection file. At the end, we had this group for class. And then we created it. Again, if you do everything right, you should not have to restart OpenNMS. It should just create these files automatically. Okay, we did the dump. Now, if we have this data, it's time to graph it. Now, if I go to, we use RRDTool, and in this example, we use this thing called RRDTool. RRDTool gallery. So Toby Ediker has an RRDTool gallery where he has a bunch of graphs that people have submitted. And so you can see these little, this is squid information, inbox 0. I've done this. I've actually corrected how many things are sitting in my inbox. I use the SNMP collector on our mail server. So tons of interesting graphs. Some of these, I like it when you do kind of this kind of faded level here. There's some gorgeous graphs in here. I like the kind of blue with the shadow drop and stuff like that. Anything you see here, you can create in OpenNMS. So you can create that graph here. And what happens is, we use the RRD tool syntax for creating graphs. You can display a single variable on a graph or multiple variables, and you can perform math and things like that. It uses a technology called reverse Polish notation to do that. And with some creativity, you can create some really cool graphs. And graph definitions are stored in this snmp-graph.properties.d directory. So it's a .d directory, which in Unix speak is usually if you put something in there, it is automatically enabled, and the same is the case here. So here's a bandwidth utilization graph. Where there's a gap here, this is where there was no data. So for whatever reason, there was no data. We didn't store any data here. So how would you want to create a graph like this? Well, we're going to use, in this case, we're using the high speed counter. So we're going to use the IFHC in octets for here and the IFHC out octets for the green one. So this happens to be one of this reports called the HC high capacity bits report. It's built on the old mib2.bits report. And this is found in opt OpenNMS etc snmp graph properties.d. It's in a file called mib2-graph.properties. So in mib2-graph.properties at the top, let me just bring it up. snmp-graph.properties.d. I look at mib2-graph.properties. So you can see you have this reports line. And this lists all the reports that are enabled. This is kind of useful. If you're working on a report or you have a report you don't want to see, you don't have to necessarily delete it. You just remove the reference to the reports line. And notice it is a line. This is a properties file, mib2-graph properties, which means its variable equals value and it's terminated with a carriage return. So reports is the variable name equals mib2 HC bits, comma, space. This backslash is a line continuation character, which means treat everything as if it was all one line. One of the biggest things people will do is they'll put extra characters after that. So if I add a space, one of the things I like about Vim is you notice all of this stuff turns white. We get a different syntax check because it's not all one line. So if I get rid of that, it's all one line. So that's interesting to note. So the reports are then defined in little report sections here. So let me go back to my slide because I think it'll be a little clearer. So here's the HC traffic in-out report. This is the bit that we were just looking at. Whoop. This is the piece we were looking at right here. In-out traffic utilization, high speed. And so you have to have a minimum of 4 of these lines. This happens to have 6. So what this says is name. So anything between this dot, the first dot and the last dot, is the internal name of the report. In this case, it's mib2 HC traffic in-out. That will be the report that's listed here. As you can see on this very bottom of this screen here, HC traffic in-out. So mib2 HC traffic in-out is this report here. Now the name, which will appear in the GUI, is called in-out traffic high speed. You probably won't see it unless you mouse over. You won't see this particular report. Skip suppress for a minute. Columns. IFHC in octets, IFHC out octets. So in order for this report to run, it's going to go and look for a file called ifhcinoctets.rrd and a file called ifhcoutoctets.rrd. If it finds both of those files, it's going to attempt to do the graph. Now the type tells OpenNMS where to look for these 2 files. If it's node SNMP, it looks for it at the node level directory. So that would be that /66 or /1. It will look for those files there. If it's interface SNMP, it's going to look for an interface directory. So like in the case of the Juniper switch where we had a VLAN 1, VLAN 2, and we had Gigabit Ethernet 0-0-0, it's going to look in that directory. If you have a generic resource such as disk index or something, you put the type there. That just indicates where in the file structure OpenNMS should look for the RRD files. And then we run this command. So we have in-out traffic utilization high speed, percent utilization, etc., etc., etc. So if you look at this graph, in-out traffic utilization high speed, this goes here, vertical label is percent utilization. Go over here. Vertical label is percent utilization, etc. Now, in order to extract the array of data out of these RRD files, we use this def tag. So we define a variable called octet in, and we define a variable called octet out. This says go to RRD1. Anything in curly braces is something OpenNMS provides. So curly brace RRD says in RRD, this would be the full path to the RRD file. So this would be something like /ops/OpenNMS/share/RD/1/VLAN1 -MAC address /ifhcnoctets.rrd. So RD1 reports to that column, RD2 corresponds to that column. Now in that file, you're going to grab a variable called ifhcnoctets. Now this, in OpenNMS, 99% of the time, this is going to match this. This says go find this array file and then look inside the file. It is possible to store more than one variable in a single file. And in that case, you would refer to RD1 and then grab the different variable out of that file. But in this case, it says go to the RD1, grab an array of ifhcnoctets variables, values, and then go to RD2 and grab an array of ifhcoutoctets values. Now we're going to do a little math. So in this case, we're going to create a computed or a complex definition. Computed definition said %in equals, and this is reverse Polish notation. So this is octet in 8 and times. Now I don't know if you guys are familiar with reverse Polish notation. So let me, usually you use algebraic notation. So if I wanted to multiply 2 times 3, I would do 2 times 3 equals 6. Not so with reverse Polish notation. Reverse Polish notation uses a stack of registers. So I type in 2 and I hit enter, which pushes 2 up on the stack. And then I hit 3 times. Now when I hit the time key, it's going to multiply the 3 times whatever's in this stack. So it goes to 6. If you've ever used HP calculators, you've probably become familiar with reverse Polish notation. I personally love it, but it can get a little confusing. But what this says is take whatever is in this array, octets in, multiply that times 8. So octets in 8 times. Now this is going to be in megabits per second. So this is in bytes. So this turns it in, by multiplying by 8, turns it into bits. Now we want to represent bits as megabits, because that tends to, it's 10 meg, 100 meg, a gig. We want to represent it as megabits. So we're going to divide by 1,000,000. So we'll take octet in 8 times, and then we'll take 1,000,000 and divide it by. So that'll give us our values now in megabits. Now again, ooh, curly braces. If we have curly braces, this means something that OpenNMS is going to grab. In this case, it's going to grab the value out of this report line of IF high speed. IF high speed happens to be a string that we gather. We don't graph, we don't collect IF high speed because it doesn't change. You know, if you're a 1 gig circuit, you don't just suddenly become a 88.7 meg circuit. You know, so we just store that as a string variable, and this allows us to go to a file called ds.properties where we store our strings and grab that value and include it in the math. So this says, okay, we've got our bytes times 8, turn it to bits, divided by 1,000,000 turns it into megabits, divided by the high speed gives us our percentage. Now we have a ratio of how the total interface speed divided by how much is coming in. We multiply that times 100 to get a percentage. So now we have the percentage of in, percentage of out. And then to make the graph, we decided a while ago that outbound numbers should be represented by a negative number. So we create this thing called %out negative, which is 0 minus %out. I could have easily have done -1% out times, so I could have multiplied by -1. But this is just a different way of representing it. Now I'm going to create an area graph. The comment here just gives us a blank line, and I'm going to create an area graph on the screen that says take % in and graph it with this particular color. So if you guys are familiar with RGB colors, red, green, blue, if you've done any web page design, you've probably seen this at least. These first two numbers go from 00 to FF, representing no red to very, very strong bright red. So FF would be a very, very bright red. So there's a little red, 27. There's a little red. AA is very strong green, and E is is an even stronger blue, which is kind of funny. So what we're going to end up doing is representing this as kind of a blue color. And then for the out, we're going to graph out neg, the negative number, and this is going to be a stronger. It's got 8D as the red, C6, which is a lot closer to FF for the green. So this is going to be a much greener number. And you can choose your colors. And then finally, we're going to graphically print the values of the average, min, max values here, average, min, and max values of these arrays of numbers. So the average inbound traffic here is 4.74 meg. Min is 1.16. Oh, it's percent. So it's 4.74%. The minimum is 1.16%. Maximum is 18%. So outbound, I'm 18% utilized, and inbound, I'm 46.79% utilized at the maximum. So that's kind of cool. Now notice this is actually this command. There's actually a command prefix. So I want to demonstrate that. So let's go. Let me go to my node here. Let's do resource graphs. Now, this thing hasn't been sitting around for a while, so I'm going to actually graph it. So, as I said, I didn't start this VM until I got ready for the class. So here's our graph. Here's our bits in and out high-speed graph. Let's go find the traffic utilization graph. That's boring. So let's go back up to in-out. There's so little traffic here that's kind of boring. So here's my in-out graph. Now, if I go to, let's clear this. If I go to opt OpenNMS Etsy, there's a file called SNMP graph.properties. SNMP graph.properties, not the .d one. So let me edit that. And in it, you will see there's the command prefix. If you take this command here, user bin RRDTool graph, blah, 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 and you add this half of the command, if you ran that from the command line, you would create a graph. You would create a PNG file that had that graph. Now, we don't do that. We use a library, so we're not actually spawning a shell and running it to create a graph, but it gives you, we use that syntax in order to do the files. So I can make changes here. I can add stuff to make these graphs kind of funky, but I can also modify the command prefix to affect all graphs. So I'm going to add here, I'm going to go in and I'm going to put in -- color canvas 1, 2, 3, 4, 5. So I'm going to make the background canvas. Again, this is long enough as it is, so I'm not going to go through all the stuff you can do with RRDTool. If you go to the RRDTool site, which is pretty good, you can look at their file. And if I create the canvas there, and I go back and I hit refresh, oops, did something wrong. So notice that there's an error, so this isn't working. So what did I do wrong? I left off a 0. So it didn't know what to do, right? There's 6 zeros. So let me save that, go back here. Now rescan. Yay! So now I've got a black canvas. And if I go back here, graph all of them will have a black background. So I can create, using the SNMP graph.properties, I can globally change things. So I don't have to go and edit all the several hundred files that we have here to create the graphs. Notice that I don't, once the graph is created, once I've actually created the graph, I don't have to restart. And so let's go and put that back. I don't really like that. It just makes a great example. So undo, and I will save that. And then we'll go back here and hit refresh. It's back to white. So just something to think about. Now, Let's talk about our graph. So our graph is very, very simple. We're going to call it class collect, call it random collection example. We're going to do this. It's going to have a column of class random. So remember, class random is the name of the RRD we created. Oops, I thought I had a slide. There it is. There's class random RRD. So I'm going to go and create that. And then notice the value. I'm going to print a line. And again, line 1 is a thin line. Line 2 is a medium line. Line 3 is a thick line. So this is going to have no red, no green, blue. So this is going to create a bright blue line for the random value. Now let's do this. So I'm going to go here. Well, let's go back to the class. The other file in exercise 10 is this class-graph.properties file. I'm going to copy that link. And I'm going to go to SNMP-graph.properties.d. Here's all of, we do tons and tons of graphs. I'm going to wget that file. Boom, got that file. So now, when I go back to my particular device, I'll go to localhost. I'll do a resource graphs. Because we used instance 1, that's a scalar. It's a node level graph. So I'm going to go ahead and graph it. And if we go down, it should be at the bottom. I think I have to restart. Let me just double check. So class saved, cat. So there's our file. It's reports for class. It's looking for something called class random. It's here. Oh, I do have to restart. I have to restart because once the file is in the system, in the web server, it knows about it. I can change it, but I actually have to restart here. So OpenNMS bin, OpenNMS stop. And then I'm going to restart. Now, when this is restarting, I'm going to play with, I want to show you another graph that I really like. Again, I'm just throwing that out for total extra credit because it's one of the most complex graphs we have. But there is a graph that does, I talked about it, this is CPU utilization. So if we go back here, all the way back to the beginning of the lesson. Whee! This graph here, the CPU statistics, I really love this graph because it's useful because it's giving you information in two different ways. You can see the load average. So you can see it's a little, the 1 minute load average is a little spiky, which means that there are processes that go up and down, but on average, it's a lot smoother. And then you get the CPU utilization. If I see a high load average with a high CPU, like a bright red underneath it, then I know I need to do something. That is in the net SNMP file, and it's the CPU usage full graph. So if we look here, we're going to grab a ton of information: interrupts, user, wait, nice, system, kernel, etc. So it's going to go to the node here. It's going to go to the node level, and it's going to look for these RD files. Does it have this file? Does it have this file? If you look up here, here is CPU usage, which is missing interrupt user raw wait. No. Oh, soft IRQ. So some agents support this variable, some don't. So what ends up happening is this CPU raw, so it'll try and print this graph. It'll print this graph if these exist. If this one, if it happens to have the extra value, the CPU raw soft IRQ, this suppress line will make sure that the other report isn't printed. If I go back to the slides, I kind of left that off on the disk I/O one, the utilization one. If you guys remember from our SNMP lesson, the high speed graph is our 64-bit counters. It requires that 64-bit counters are supported and that the device supports SNMP version 2. Otherwise, you get the 32-bit counters. Well, you don't want to print out both graphs if you have the high-speed graph. So what you can do is, in your graph definition, you can suppress. See this second line here, suppress. So this is the HC, or high-capacity traffic in-out graph, and it'll suppress the normal in-out graph. And so that's what's going on here. So it'll suppress the CPU uses graph. So we grab all these, we do some calculations, and then we do a print. Oh, that's not the one I wanted. What's the one I want? Stats full, maybe. CPU stats full. Yeah, so this grabs the load average as well as all the CPU information. And then it prints out, so here's all the definitions, here's all the complex definitions. And then this is what I really like. You can put if statements in here. And so the way we get those cool stacky graphs is you're basically going to print out 10 graphs where if the CPU is within a certain range, you print out the value for the 15-minute load average. And if it's not in that range, you print out 0. Does that make sense? It's easier to draw on a whiteboard, but I don't have a whiteboard right here. So the idea is if you're 0 to 10%, you'll have a graph. If it's above 10%, you'll just have a line. So you create that graph in a particular color. And then you create another one for 10 to 20, another one for 20 to 30, another one from 30 to 40, etc. And then when you pound them all together, you get that nice little stacky graph. Isn't that kind of cool? I think that's kind of cool. Again, there's lots of cool stuff you can do with RRDTool. So let's log back in. Look at resource graphs. Click on node level performance data. And there we have our random value. So as you can see, it's a blue graph. You know, the minimum value, maximum value, average value, it's printed out here. Not very exciting. Now, if I actually clicked on something that is kind of exciting, is we've got this thing called the near real-time grapher. So I have to wait 5 minutes for this. So suppose this is a temperature alert. We've opened up the door, we've turned on fans, we've turned the air conditioner down, we've tried to cool down the system. I might not want to wait 5 minutes to see what the temperature of the server room is. So I can hit the near real-time grapher, and it'll actually go out and instantaneously grab information. Now the default interval is 10 seconds. I'm actually going to increase it to 1. So you can see now every second, boom, 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 we're getting the average value. So we're doing the SNMP data collection and we're graphing the average value. Now, as extra credit, can anyone tell me why these things plateau for approximately 5 seconds? If you were paying attention, let me kill this. If you were paying attention, back here when we actually did this, the NetSNMP extend command caches, extend cache time values for 5 seconds. That way you can't kind of denial of service your server. If this is an expensive query, you can't denial of service your query by just pounding it with SNMP requests. So, so that's why it was every 5 seconds. So that's about it. I think I've been rattling along for quite some time, but we've got our graph. Again, this matches to what we've defined here. Just print the title random value. This is about the simplest graph you can make. And then I talked about the near real-time grapher. So near real-time grapher allows you to basically do the same report, but circumvent it and do random values. Now, random value uses a library called backshift. And backshift is, for Newts, we don't have the RRD library to rely on to do graphing. So Jesse White wrote a JavaScript graphing library called backshift, which implements most of the RRD syntax. And so when we do the NRT, we actually do it using backshift. You get backshift as the default with Newts, but you can go into OpenNMS properties and change it if you'd rather use backshift. It may require a restart. I'm going to do it. I know this lesson is getting very, very long, but it's kind of cool. So I'm going to edit OpenNMS.properties. And I'll look for backshift, and here we go. So by default, it uses auto, so it will actually use the PNG graph for RD or Jrobin, and it'll use backshift for Newts. If I comment this out, it will use backshift. And I think, yeah, it will require restart. So opt OpenNMS bin, stop. And then I'll start it up. Now, the next lesson, the final lesson, so if you've worked your way, you're up to lesson 11, the final lesson in the OpenNMS 101 course is thresholding. So now that we've got this data, we want to apply some thresholds to it. It should be fun. And then I'm going to start the OpenNMS 102 courses, which will be standalone. So if there's something you need to review or extend on, you don't have to listen to me go through all this other stuff. So while that's restarting, let's kind of zoom back through this presentation. So performance data collection, we have tons of different types of collection. SNMP, JMX, HTTP, HTML, blah, 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 blah. And in any case, you're going to somehow go and use the protocol that's supported to collect a number or a string and store that in OpenNMS. Do lots of pretty graphs. We use RRDTool, which is a round-robin database, which means you create a circular database so that the oldest items fall out when the database fills up. Plus side is that it's small and fast. Downside is you can lose data older than a certain amount of time. These create RR arrays. By default, OpenNMS does as polled 5-minute samples for a week, hourly samples for 2 months, and daily samples for a year. This is the RRDTool dump command. We talked about the file locations. Response time is stored under IP address. All other data is stored under node ID or a generic resource under that. Newts is an option if RD is not fast enough for you. Again, we have customers doing data collection on millions of devices into Newts, and it's pretty much limited by your budget. You know, how many servers you want, how many disks you want, how much redundancy you want. So SNMP data collection is all data collection is controlled by the collectd file. So we have a collectd. In the case of SNMP, it points to a collection schema called default. That is going to be in a data collection file that is specific to the particular protocol. It's data collection config for SNMP, and then the protocol name dash data collection for the rest of them. So HTTP, JMX, JDBC, etc. The data collection file consists of your RRD configuration, how much data you're storing for that particular schema, and what data collection groups are included in that schema. Data collection group has object IDs mapped to groups, and then groups get mapped to system definitions. We have scalars, which are numbers. We have interfaces, which are indexed by IFIndex, and then we have the ability to do generic resources. Here's some examples. Oh, there is a coffee maker MIB. OpenNMS does support it, so if you happen to have a coffee maker, we will go out and do coffee maker collection. I've never seen that, but it's there. I want to make a soda MIB for my soda MIB thing. So we've added we created a new source for SNMP data using class collect.shell. We added that to the extend. This gave us the ability to collect information out of a particular object ID. We mapped that object ID to a group, mapped that group to a system definition, mapped that system definition to the data collection file, which enabled it. Boom, we collected data. Class random.rrd was created for the RRD file. That's the round-robin database. As you see, it's about 38 kilobits. And then the meta file, I'm not quite sure what it does. I know it's used for the near real-time grapher. You can do RRDTool dumps, see this information. Then we talked about graphing values. We use the RRDTool graphing, and then we went and graphed our random value. Now, if I go back here, I should be able to log back in now. And I hit resource graphs, node level performance data. And now we're using backshift. As you can see, it's very, very similar in output to RRDTool, but it does have the ability, you can mouse over things and actually get values. So in this case, that's 18.5K, that's 16.5K, that's here. You can click on the data tab and get actually the raw data. So you can see these are all the data points that make up this graph. And again, you can use this with RRDTool. I think it's kind of cool because of this part. So you can use this with RRDTool, but by default, we're going to use RRDTool's graphic. Now, the one caveat is everything that we ship with OpenNMS is mapped to Backshift. So all the OpenNMS default graphs work with Backshift. If you create your own and you're using some weird RRDTool commands, they may not work. So the graphs may not look the same. Just a caveat. Anyway, that's it. That's today's lesson. That's data collection. So now we've covered the big four. I hope you folks found this useful. And tune in for the next one, which will be lesson 12, which will be on thresholds. Hope you guys find this useful. Please give us some feedback and talk to you later.